Hello and welcome
Crofton.
to Stocks Down Under. Today we're joined by Arye, Kohavi, and Kevin Crofton. Arye, you're the chairman and CEO of the company. Kevin, you're director of Adisyn. So the story needs a bit of explanation because Adisyn itself is not the company that we're here to talk about today, but we're here to talk about 2D generation, which is something different. So first question is, can you sort of explain the company structure and also explain how 2D generation fits in?
Well, it's really quite a simple description, really. Adisyn is two-pronged. As you know, it's a services business that is actually generating revenue in Australia already. And then there's the strategic play that is going on right now with 2DG. And frankly, that's the strategy of the company, is to focus on 2DG for the long term.
Right. And so in terms of 2D generation, can you explain what problems 2D generation is trying to solve?
The company is dealing with a material called graphene. Graphene is defined as wonder material because it has unique capabilities in aspects of conductivity, thermal deposition, and more. This is one side of the story. The other side of the story is the interconnect. Inside any chip in the world, there are the transistors that are doing the job, and there are the little connection between the transistor. They call it interconnect, the interconnect between the transistor. Right now, or in the last 10 or 15 years, all the interconnect is done by copper. Copper is a good conductor, but it has two problems. First is copper is doing diffusion into the silicon. So you should wrap it with a diffusion barrier that will not allow the copper to go into the silicon. And because the diffusion barrier is in a constant size, when the generation come further and the interconnect becoming smaller and smaller, and the diffusion barrier is constant, the bulk of copper you can put inside become something that it makes this copper almost a non-metal. So the main issue, the second issue is that right now, what limits the world to go ahead to further generation to 2 nano and beyond is the interconnect. It's not the transistor. You can put much more transistor over the surface, but the interconnect are so thin, so they generate a lot of heat. And because of that, when you design a new chip, you put less transistor than what you can because of the problem of the interconnect and the heat generation. This is the issue. It's not a minor problem. It's one of the cliffs of the industry. In any conference you're going in the aspect of semiconductor, one of the three main topics will be we should solve the issue of interconnect. Otherwise, we cannot go further. It's a cliff of the industry. Graphene is defined as the solution for that. But because graphene is very, very conductive, even in a very, very thin layer, in a layer of the thickness of one atom. But graphene is made at 1,000 Celsius. And if you put the chip under 1,000 Celsius, all the chip will melt. So the big problem of most of the academic companies is how to produce graphene at low temperature. How can we bring the graphene into the semiconductor world? Because 1,000 Celsius cannot work, and you should be below 350 Celsius, something like that, the limits of the industry. The headline of what we're doing is that we succeed to grow graphene at low temperature. And when it will be an operating technology, it will enable the world to go to further generation in the semiconductor. This is what we're doing.
I think that I would maybe add a quick comment. You know, the problem that Arye described is that the current copper interconnect has significant limitations that prevent the industry to move below a 2 nanometer design rule. And as a result of that challenge, companies have been investigating all sorts of solutions, none of which are elegant. They all are costly to bring into a manufacturing environment. The nirvana for the industry would be to be able to put down an alternate material to copper currently being identified as, has been identified as likely to be graphene, and to be able to do it at low temperature that's compatible with a production environment. That's the simple situation that we're trying to deal with in the industry.
Right.
And we have to unlock that. That's what we're doing.
Yeah. So just to follow up on that, currently, I think TSMC, Samsung are sort of starting up 2 nanometer facilities. Of course, they're looking at beyond 2 nanometers. So Intel with its 1.8 nanometer is hoping to get into production if they manage to do that at some point. But are you saying that going actually below 2 nanometers is a hard wall if this type of technology isn't ready by then?
Well, sorry, Arye, can I take that question?
Yeah, please.
I would say it, Mark, I would slightly modify that a little bit. We know we can get functional devices even at below 1 nanometer. That's already been demonstrated at IMEC, for example. The tricks to get there using extremely costly photolithographic processes, it's prohibitive. It's cost prohibitive in a commercial environment. We know we can do it with splicing. Okay, also very, very costly. So it's not a question of can we? Yes, we can, but it is not a commercially viable solution, number one. And number two, even still, copper ultimately becomes limited in the physics side of things. And we know that it's going to run completely out of gas. And as a result, there has to be an alternative material that's been brought forward. Yes, TSMC has announced they'll go into production at a 2 nanometer design rule. For sure, they're going to do that at the end of this year. However, right now, it's a very costly process, and it's going to be limited to very few users. Perhaps Apple at their A18 Plus processor, and at the AI-specific chips that are being produced nowadays as well. But it's not ubiquitous.
Yeah. Okay. And so you're not the only company developing or working with graphene for this specific application. Can you talk a little bit about the differences between what, basically in the approach, I guess the approach to tackling the problem compared to some of the others?
Yeah. Graphene is made throughout the world with a technology called CVD, chemical vapor deposition. The original CVD needs 10,000 Celsius, 1,000 Celsius, and it's not relevant. So the industry believe that if they add plasma to the CVD, what is called plasma enhanced CVD, it will enable the graphene growing at the reasonable temperature or the allowed temperature. Most of any company in the industry, or most of the biggest one, TSMC, Applied Material, all those invest a lot of money trying to solve this issue by the machine plasma enhanced CVD. And they failed. We know that until now, nobody succeeded to grow graphene at low temperature, a quality graphene. And we know because we have partnership with IMEC, and we know because we hear from the industry, And we know because the original reason we established the company is approach from one of the biggest saying, okay, we probably failed in the plasma enhanced CVD, try to find another technology. What we're using is totally different machine. It's called ALD, atomic layer deposition. It's a machine that exists in any fab in the world, doing more and more depositions, currently metals. It's a machine that's being sold more and more because when the generation become or the needs are for thinner and thinner layers, the ALD is more in use. So the main turn that we did that is to use this machine and not this machine. And we were the first, and we can probably say we are still the only trying to use the ALD to grow graphene. Because we were the first, we were able to submit a lot of patents around that. Any combination between the word ALD, the word graphene, and semiconductor, I think it's under our patent. We're getting calls from the industry, from the biggest companies in the industry, saying we approach you because we haven't found anyone else in the world using ALD to grow graphene. So this is our uniqueness. And we believe that because we use something very, very unexpected to use ALD for graphene, it's, for the ones that coming from the industry is like you're using a hammer.
Right.
So
right.
This is the issue. This is the turn that we did. Nobody else did.
And so following on from that, can you talk a little bit about your R&D roadmap? So what needs to happen between now and having a demonstration or a demo model ready, basically, in demo chips?
Now, the main challenge is to grow high-quality graphene at low temperature. This is the headline of what we're doing. We have a very, very skilled team, most of them PhDs, that coming every day to work and try several parameters. What is the heat of the surface? What is the heat of a precursor? What is the pressure? How much time do you let it go down? What is the raw material? There are several raw materials. So our R&D plan is to find the right combination to grow graphene. It is all led by Paul Rich. Paul Rich is British. He used to work for Kevin for 20 years, something like that in SPTS.
Okay.
They did amazing things together. So Paul is our technology leader in the last almost 3 years. And what he's doing with the team is to find the right combination to grow graphene. What we have problem until last months, is that we're using a very basic ALD machine. It's a machine we bought several years ago with a low budget, and it has limitation like it doesn't have plasma, so you cannot treat the surface before deposition, and many other limitation. So because of the fundraising, we bought new ALD machine from one of the leading company called Benek from Finland. It's going to be installed on May in our facility, and we are excited about that. In parallel, we found a few weeks ago another ALD machine about the same type in Tel Aviv University. Tel Aviv University has a very significant nanotechnology center. So we signed a strategic cooperation agreement with Tel Aviv University, and we're using their ALD, and we're using other tools that they have and know-how that they have over there. So we can, I will not say double, but very, very fasten the R&D process, because now we have two ALD machines, advanced ALD machines working for us,
All right.
even three if we count the old one. So the plan is to find the right combination to grow uniform graphene. We already demonstrate that we are able to do it. We grow graphene at low temperature with all the limitation. What we haven't proven yet is to grow a uniform graphene, to cover all the surface. And this is the challenge we got from the big ones, from all the Applied Material, the TSMC, ASM, and so. And this is the challenge, this is the proof of the technology the industry is looking for. When you develop technology, there is a T-turn, if it works or doesn't work. We already turned that, it works. We grow graphene at low temperature, and now we should know how to control it, how to grow uniform graphene over a big surface. This is what we're working for. The original plan was to do it within 18 months. Now, when we have two ALD machine, it will be shorter, and we're pretty sure that we're going to do it and have it pretty quick.
So let me jump in there, please. There's a couple really key points that Arye made that we need to be clear. We have been able to show that we can grow graphene, high quality graphene at low temperature. It's in isolated wells. It's not over even a 1 centimeter by 1 centimeter coupon yet. So first principles, we are able to do it. That's done. We know we can do it. Our objective is to then scale that to coupons, then ultimately, in some cases, for a wafer level processing. He also said that there are multiple inputs. This is a process, a recipe that we're trying to generate. There's approximately eight major inputs that go into this process recipe. Ultimately, what you come out with is the process recipe the size of a softball, or is it the size of a basketball? And the wider that process window is, the more compatible it will be to go into a manufacturing environment. We don't know that recipe. And so the science is going to be generating that recipe, finding the right inputs. What is the actual bandwidth of each of those inputs to deliver a result? And of course, the wider, the better. That is the work that has to be done over the next 18 months.
Okay.
I'd also be very cautious about saying we're going to accelerate anything at this point. We're on the path to doing something by an 18-month window. And we should know what we have in that time frame.
Right. Okay. And so, Kevin, you've got a very extensive background in semiconductors and in manufacturing. Yeah. So this is probably a good question for you. And this goes to the point of commercialization once you get to that point, right? What does a plan look like once you get there? But also, what is the market opportunity? Because I'm pretty sure investors are really curious to find out a bit more about that.
That's a great question. Look, there's a number of opportunities for how to capitalize on this potential solution. And you can think about a licensing arrangement. You can think about some sort of co-process development and then licensing. In my opinion, and this is only my opinion and that of the board and the team, it's unlikely that we'll ever get to a revenue generation, in my opinion. It is very likely that we are going to demonstrate real performance that solves a massive problem in the industry, and it will likely be a company. And Arye mentioned them earlier in one of his Q&A answers. It could be one of the large capital equipment manufacturers. It could be a large device manufacturer that they will want to buy the technology and buy the access, and either exclusively or on a non-exclusive arrangement. And that's ultimately where where we, as a board and as our shareholders, we're going to have to be thinking about what is it, how do we capitalize on it, what's the return, and we go from there.
Right.
But I'd be very surprised if we ever get into a real revenue generation situation. It's
Right.
too critical for the industry.
So
which is kind of a segue into the second part of your question.
Mm-hmm.
The interconnect problem, especially when you think about AI applications, autonomous drive vehicles, when you think about even anticipating human interaction, for example, that requires extremely fast processing capability. And the only way you'll unlock that is with a change in the copper interconnect. And that gives you potentially the ability to unlock literally hundreds of billions of dollars worth of revenue in the industry. That's the issue. That's what we're looking for.
Yeah. So when it comes to
investors, I will tell a story. I had a conversation with one of the managers of one of the leading global equipment manufacturer. And he asked me, how much does your company worth? And I told him, how much does it worth for you if your equipment will be the only one that will be able to grow graphene and enable Apple to go to iPhone 20? And he said, for me, it worth anything. So I told him, so this is the valuation of my company as well. If our technology enables that, that's the worth, the valuation of the company.
So if I understand correctly, the opportunity for investors specifically would be about getting the best price in a M&A scenario then. Is that right, Kevin?
That's exactly right. That's exactly right. And as Arye mentioned in another story, it is the problem in the industry to be solved. And it ultimately, if you look at all the biggest capital equipment companies, it's equally of value of the same again of those companies, equally. So
right.
it's quite a large oyster that we're talking about here.
Okay.
I would say I would say, because we had several discussions with several giants, the ordinary course of business that they are doing is when they convince that your technology fits them, they're usually doing integration into their machines, and in parallel buy 25% of the company, a third of the company, because they must have a hold inside the company. Those evaluations are 10, 20 times more than what we are traded right now. And then when they are major holder, we are going together to the customer, to TSMC, to Intel, if it's not themselves. And then after the integration, and I agree with Kevin, usually before sales, they buy all the rest. They make an offer in another gap of the valuation and buy all the rest of the share. This is their course, and I believe that's what's going to happen.
Right. Very exciting. So
Yes.
That brings me to the last question, because before you get there, you'll need to demonstrate a couple of things. So if we look at milestones for investors, what do they have to look forward to? What can they look forward to in the next 18 months? We talked about that time frame, 18 months. So let's talk about that time frame now as well. What can investors look forward to in terms of news flow, in terms of achievements, accomplishments, etc.?
I will split the answer to several routes. There is the technical route. In the technical route, we believe that we'll announce the progress, meeting the targets, and all this technical route is something very, very promising. Then we have another route of patents. We're probably get approval for some of our patents, a final approval, or US approval, European Union approval, in the next 18 months. each patent approval is very, very significant because it blocks a territory. And there is the root of the corporations. When we're progressing, we can team with world's leaders, companies, R&D institutions, other players that needs this technology. So we believe that in the next 18 months, we'll sign several significant cooperation agreements with companies and institutions that needs our technology. And each one of these cooperation is the lead to generate buyer of the company or buyer of the technology.
Right. Okay.
Kevin, if you want to add.
I think you hit it on the head. I mean, I think about it in a serial process, and I would remind everybody who's listening to this interview, we're a very, very small company, and we already have a relationship with IMEC, for example. We just recently announced the Tel Aviv University relationship with their Nano Center. I would expect that we'll see more of those types of R&D type of organization. Those relationships will continue to expand in number and probably expand in scope. We'll see that happening through the next 18 months. Sometime in the latter half of that 18-month period, we should be able to have demonstrated enough success that will get the interest of at least one capital equipment collaborator. That would be a very forward type of program and an announcement. And then, of course, somewhere in that time frame, we will also be able to announce that we've done an integrated device, not a TSMC integrated device, but a facsimile thereof, perhaps out of a Leti or an IMEC or another, that will show that we can actually integrate it into a functional device. So there are stepwise things that have to happen over this period. And as Arye said much earlier in this interview, you can't schedule science. You can't. The science has to occur. And we have so many unknowns that we have to go and address that our investors are going to have to understand that we're on that path, but they're also going to have to be patient to understand that we have to do the science that gets behind us.
Well, exciting times ahead, gentlemen. Thank you very much, Arye, Kevin. Thanks for your time.
Thank you, Mark. Really appreciate it.